Okay, Assalamualaikum and good afternoon. So for today, we continue what in topics boundary layer. So yesterday we learned about the boundary layer, and I think you already know about this one. So the connection between what we learned previous chapter and here is in boundary layer we need to use the velocity distribution that occur inside the boundary here to calculate the shear stress, because shear stress is the only parameter that it is a little bit difficult to be measured. Okay, and yesterday we stopped at this slide. So I already explained what is boundary layer thickness. So it is the physical thickness, so means we could measure the thickness of boundary layer from the experimental works, and the unit for the boundary layer thickness is in meter or millimeter. So means it is a length of the thickness. So in mathematical expression, so we could write the boundary layer thickness like this one. So means that the boundary layer thickness delta is actually the value in y-axis. So which is from u equal to 0 until u equal to 99% of the free stream velocity. So I hope you could write you could understand the meaning of boundary layer thickness, as well as you could explain the formation of boundary layer. So and then because the mathematical expression of boundary layer here is very simple, it is just the value of y-axis. So means we cannot calculate the boundary layer thickness straight away. So we need to use a few equation to calculate the boundary layer thickness. Okay. So next to calculate, to develop equations for boundary layer. So first we need to know another two parameters, which is displacement thickness and the momentum thickness. Okay, now I would like to explain about the displacement thickness. Okay, the symbol of displacement thickness is delta with a star like this. So okay, so I hope you could write a delta, and then you have a asterisk sign on it. So this is the displacement thickness. So the definition is the distance the surface would have to move in the y direction. Okay, so to reduce the flow passing by a volume equivalent to the real effect of the boundary layer. So from the definition, you know that this is the distance, because thickness is a thickness. So it is, but the displacement here means a distance that you need to move in y direction, still in y-axis, to reduce the flow passing by a volume equivalent to the real effect of the boundary layer. Okay, so the idea, the simple explanation of this one is actually, as I said, we want to calculate the boundary layer thickness. However, the equation of boundary layer thickness is very simple. It's just a value in y-axis, so we cannot do any calculation with that equation. So then we need another few equation to help us to calculate the boundary layer thickness. So before we could create that equation, we must make sure that our calculation is fulfill the idea of conservation of mass. So means that the the displacement thickness here is actually the a test or the verification of our equation to make sure that our equation is actually conserved with its mass. Okay, so we could see we could explain the displacement thickness like this. So for example, we have a flat plate here, and then this flat plate there is a free stream velocity here. So its flow before the plates and after a certain distance, so uh, it start to touch the flat plate here, and then it will create a boundary layer. So please remember that the idea of boundary layer is the thickness from the surface here to the velocity, which is 99% from the free stream velocity. So means here this is we have a velocity distribution here, as well as the velocity distribution at this area. Okay. So and then what is the meaning of displacement thickness is, for sure, if we see the area here, so we found that this is the mass that flow before it's going to contact with the flat plate. So however, when the molecule of fluid start to contact with a flat plate, and it create a velocity distribution like this one, we found that the velocity distribution is actually shaped like this one. So means that the mass before, so this is the mass of before it's entering the flat plate, and the mass after its flow on the flat plate is not the same. So means that it is weird when we start to do physics calculation, but the conservation of mass is not fulfilled, it's not conserved. So what we need to do is we must make sure that conservation of mass will be fulfilled. So what we do is we take the the this area, okay, and then we change the location into this area. That why, because we change the location, so that's why we call it as a displacement thickness. So we imagine there is a imaginary thickness on the velocity profile that that will be equal the mass before the fluid enters the flat plate. Okay, that's why we call it as a displacement thickness. Okay, so the main purpose of this calculation is actually to conserve the mass of the fluid. Okay, so the idea is, we need to calculate the mass. Okay, so we know that the density here is mass over volume. So what we need to do is to calculate the mass. So we are calculating rho and volume. And this volume is actually, it is okay for us to calculate the volume of this area. Okay. Then to simplify our calculation, we could imagine that the width of this one, because you know volume means it's three-dimensional, we need to have x, y, and z. But to simplify our calculation, so we assume that the thickness of the width of this plate is actually constant. So we could cancel left and right terms of the width, or we just assume that the width of the plate here is equal to 1. So mean it is equal to 1, so we could reduce the term in our calculation. Okay, so to calculate the mass here, so it is okay for us to use the idea of rho times V. So, and then the V here, the volume is actually the length times height and also times width. And then we assume that the width here is equal to 1, and the height here, okay, the height here is actually equal to delta. So, and then the velocity here, the length is the velocity of this area. Okay, so this is the basic idea to calculate the mass for this term for this area. So, and then we need to develop the conservation of mass equation. So we found that the mass for A here must be equal to the mass for B plus the mass for C, because as I said, this area is actually come from the area of this one. So we bring the area of this, we fulfill into this one. And at this area, okay, so at this area, the velocity is constant at u, at capital U. So we could calculate the thickness of this one. So which is the thickness of this one is symbolized by the delta star, because the thickness of this one is actually reflect the displacement thickness of our boundary layer. So and then the displacement thickness of boundary layer is 100% imaginary thickness. We cannot measure it through experiment with any device because the displacement thickness is actually not exist. So the idea of this one is actually to make sure that our equation fulfill the conservation of mass. Okay, that is the purpose of this calculation. So the only thickness that can be proved in experimental work is the boundary layer thickness only, the delta. However, the equation for delta is quite simple, it's straightforward. It's just the value of y. So then we start to calculate the mass for A is equal to mass for B plus mass for C. And mass for A is, I already show you how to calculate this one. So it is become rho, U, and delta. And also the mass for C is quite straightforward. So we could calculate it as rho, U, and delta star. So if you see the diagram here, so if we want to calculate the area of this square, so it's just rho times the length here is capital U and the thickness here is delta star. So and then because we assume that the width here is equal to 1. Okay. Okay. So however, maybe we have a little bit difficulties to measure the mass for the area B, because the area B here is not, the velocity of area B is not constant. So that's why we need to calculate it, start from a small area of this one. So for mass for this small area, okay, so mass for this small area, so let's say we have a dm here. So the mass for that stripe, the colored area is rho, is times by with the small u, and it's times with the height, which is the dy. So and then if we want to get what is the total mass for this, the total mass for this area, we need to integrate both sides. So and then if we integrate this both sides, so we have the mass for area B is now is the integral of rho u and dy. So again, in integration, so we need to have limits. So the limits here is from, because we are integrate with a dy, so we take limit on y-axis here. So it is from 0 to delta, because we know that at this point, the y is equal to 0, and at this point, the y is equal to delta. So that's why we take from 0 to delta. So here, if you have, if you see this one, so this is the mass for MA, so this is mass for MC, and this is mass for the MB. And then we rearrange the equation because we want to know what is the value of delta star. So we rearrange the equation like this one. So and then we have this term, and then we could rearrange the equation of this one to make sure it has integration. So we could merge the term, so it will become like this one. So and then if we do the integral, okay, so means we simplify the equation. So we divide all terms here with rho and u here. So and then we could write it as this one. So finally, we could say that the delta star, the equation for delta star is actually this term. So I hope you could remember the equation, the mathematical expression for delta, the boundary layer thickness, and now you need to understand from where it's derived, and I hope you could remember the equation for delta star, the displacement thickness, which is integration of 0 to delta 1 minus u over u dy. So please bear in mind the small u here is the velocity for the velocity distribution, and the capital U here is the free stream velocity. So this is the local velocity, and this is the free stream velocity. Okay. So if we have a flat plate here, and this is the boundary layer, so we have the velocity distribution, and the small u is actually the velocity for all a molecule inside the velocity distribution. So however, the capital U here is the free stream velocity, which is the velocity of fluid which is not in contact with the flat plate yet. So, and then if the velocity, if you want to draw the velocity distribution above the boundary layer area, so the velocity here is also equal to free stream velocity. Why this phenomenon happen? Because you know that the velocity distribution here occur because there are no slip condition. So no slip condition reflects the shear stress that occur between the molecule and the solid surface. And then when the molecule exists far from the surface, far from the solid surface, so we found that the shear stress is actually become weaker and weaker. That's why after at certain area here, the shear stress is totally zero. So means that the fluid could flow at the same velocity. So because the interaction that only exists is actually the interaction between two liquid molecule, two liquid or fluid or gas molecule. Okay, so this is the idea and the basic equation for displacement boundary, displacement thickness. So I hope you could, you need to remember this equation. Okay, so this is the final equation for determining the displacement thickness. So which is delta star is equal integration of 0 to delta 1 minus u over u dy. And the term for this one is actually shown in this slide. So which is the delta star is the displacement thickness. Delta is the boundary layer thickness, and U is the local velocity, and capital U here is the free stream velocity. Okay, next, we are going to derive another terms of a boundary layer, which called the momentum thickness. And the symbol of momentum thickness is shown as theta, like this one. Okay. And the definition here is the distance by which a surface would have to be moved again. So means that this is the momentum thickness is also the imaginary thickness measured from surface vertically. Okay, so parallel with y axis. To itself toward the reference plane and in a visit fluid stream of velocity u to give the same total momentum as exists between the surface and the reference plane in real fluid. So the idea is actually to make sure that our equation will conserve the momentum. Okay, previous equation, so we need to change our equation to make sure that our equation will fulfill the continuity, the conservation of mass, and now we must make sure that our equation is to fulfill the idea of conservation of momentum. Okay, so the symbol of momentum thickness is theta. Okay, so we use the same diagram actually to explain about the momentum thickness. So for example, we have a flat plate here. So and then we have the free stream velocity, which is not in contact with flat plate yet. So and then after it's make contact with flat plate, so the velocity distribution occur. Okay, due to the no slip condition and the viscous effect for this fluid. So and then we top up. We add the loss area here to this one. So and previously, because we already have delta star, so we need to create a delta star here, and then we top up the area as the theta area for this one. Okay, so means that uh, you know that we need to put we remain the rectangular area that showing the delta star here, and we add a new rectangular area that show the momentum thickness. And again, the velocity for this area is actually capital U, because this area is actually beyond the velocity distribution. So means that the velocity in this area is same with the free stream velocity. Okay. And then previously we are calculating mass. So we are using the idea of rho time volume. However, for now we are calculating the momentum. And then momentum. So and then I think you already know that the equation for momentum is mass times V. So means the mass here can be calculated by using the idea of rho and volume. So the same calculation with the previous calculation. And the V here is actually the velocity that occur for that mass. So and then to fulfill the conservation of mass, okay, I think you already know that we could say that the total mass for inlet, which is the A here, is equal to the total mass at the outlet. So and in this diagram, we could say that momentum for A here is equal to momentum for B plus C and plus D. Okay, so and then we need to determine. So I think you could do this. Okay, but I just draw a table like this. So the velocity for the inlet here is capital U, and the velocity for the areas C and D here is also a capital U. And then the area for this velocity distribution here is the local velocity, which is the small u. So and then you already know to determine the total mass for the velocity distribution here. So we need to use the integration. So we write as integral of rho u and dy. So we use u here as the small u, and the integration limit is from 0 to delta, because the limit here is y equal to 0, and this is at here we have y equal to delta. So and then we do the calculation. So we write the momentum at inlet must be equal to momentum at outlet. So we write the momentum of inlet as this one, and then we write the momentum for outlet as this one. So and then to simplify this one, so we bring the value of u to the right hand side. So we have this equation. Okay, so and then we have problems here because our terms, we have two unknown terms. So which is the delta here, delta star, and also the theta. So to simplify this one, we substitute with the value of this one from our previous calculation. So mean we substitute the delta star equal integration of 1 over 1 minus u over u into this equation. Okay, so and then we could write as this term, and then we could simplify it as this one. So and then we are going to get the value of theta. So we solve this equation. finally, we could say that theta is equal to integration of u over u in bracket 1 minus u over u dy. And the limit is from 0 to delta. So I think you already know about this one. And then this is the final equation that you need to know when we are calculating the momentum thickness. So theta is equal to integration of 0 to delta u over u 1 minus u over u dy. So again, I would like to remind you that the small u here is the local velocity, and the capital U here is the free stream velocity. So please make sure that you write the symbol very well, because sometimes a student get confused with what they are writing. Okay, so this is a very simple example for do this, because sometimes we need to calculate the ratio between the delta star and delta. So for example, we give you the velocity distribution of u over u equal y per delta. And then we need to calculate the ratio between delta star and delta and theta over delta. So the idea is simple. So we know that the equation of delta star is given as integration of 1 minus u over u dy. So we substitute the value of u over u here, and then we substitute with y over delta, and then we solve the integration process, and we get that delta star over delta is 1 over 2. So at the same time, we could calculate the theta here by using this equation. We substitute the value of u over u with a y over delta, and we solve this integration. So we get delta over delta, theta over delta. I'm sorry, theta over delta is equal 1 over 6. So this is a very simple steps to get this one. But because sometimes the question asks, you need to substitute with the idea of theta equal 1 over 6 delta, because in certain calculation, so they ask you to determine what is the value of theta. So and then you need to give it as 1 over 6 delta. So so another thing that I would like to explain here is the meaning of u over delta equal y over delta. So u over u here is actually to reflect the velocity distribution. In certain textbook, they will give you in term of u is equal to y per delta capital U. I think this term of velocity distribution is quite familiar for you, because in previous chapter we already know how to derive equation from the Navier-Stokes equation until we could get the velocity equation u equal to y over h and capital U. But in certain textbook they will write y over h with v. So this is actually the when we use Navier-Stokes equation, we just focus on the velocity distribution and so on and so forth. So might be the term become a little bit different. So we have h sometime and we have v. Okay, but in boundary layer, so normally we will write u over capital U like this, and it is equal to y over delta, because the delta here is the specific term to reflect the boundary layer thickness, and the y here is the y-axis, the length of y-axis, or the length of the vertical distance. Okay, so and then so the u over u means that, so if we have a flat plate like this, so we have a boundary like this one, the u over u is actually reflect the ratio between the molecule here. So this molecule has small u, and the free stream velocity here is capital U. So means the u over u here is actually reflect the percentage or the ratio between the local velocity here and the free stream velocity. So means that if U is equal to capital U, so the ratio will become the ratio is equal to 1. So means that it's already reached the boundary, the bound the it's already at the boundary of the layer. Okay, I hope you could understand what is the meaning of U over U here. So again, please make sure that your hand writing could differentiate the small and the capital U. Okay, so that is the basic idea on the equation that we will use again and again in these topics. And then, as I mentioned previously, we aim to get the drag force and the lift force, and or at least we need to know what is the value of shear stress, because only the shear stress is difficult to get from the measurement. So we need to find what is the value of shear stress, the tau, because we want to substitute it in the equation to find the lift and the drag force. Yeah, to get the shear stress, so we use another idea introduced by von Karman, and we call it as a von Karman equation. So it's introduced by von Karman, one scientist named von Karman around this year. And the idea of this one is actually the conservation of momentum. Okay, so the idea is, again, for the free stream velocity that not in contact with the flat plate, so we assume that the velocity will constant as capital U, like this one. So and then when it's in contact with the flat plate, so the velocity distribution will create area like this one, and we say that so the area is not square as the inlet area like this one, because there is a deficit of momentum. So there is a free area here, so which means that it lost its momentum. So in physical meaning, so we found that because we have shear stress, so we know that there are no slip molecule no slip condition here. So and then this molecule will stick very hard on the surface, and it will resist. So mean it create a shear force, because we know that F is equal to tau and A. So means that the shear stress, the viscosity actually lead or create a force that resists the flow of fluid. So and then to calculate the momentum again, so I think you already know that the momentum is mass time velocity, and mass is rho time volume. So I think this is we used this idea previously. Okay, so what we need to calculate is we need to calculate the deficit of momentum. So means that we assume that we have a small strips here, because we want to calculate all the momentum for this area. So because this area is not linear, not constant, so we should start our calculation with integral. So we start to calculate what is the momentum for this small area. So let's say the momentum for this small area is shown as D. Okay, the D here. So and the equation of this momentum is mass time velocity, and then we know mass is rho time volume and time velocity. So and then we know that the volume here is, so the length of this one is U over U, capital U minus U. Okay, because the total length is U, and the length of this one is small u, so means the length of this stripe is capital U minus U, and we need to time with B. So B is actually the width of this one. Okay, B mean width, and then we time with the thickness of the stripe. So that's why we time with dy here. So this is the mass, and then we need to calculate, we need to multiply with the velocity again. And this velocity is actually velocity reflect the velocity of the molecule at this area. So please make sure that you take the velocity of that molecule, because we want to calculate the momentum, and the momentum is actually comes from that come from the motion of that molecule. That's why we take this velocity is u, so we time with a small u again. So that's why we get this equation. So I think you could derive this one. So and then we solve this one. So we found that to get the total momentum deficit, so we integrate all of these equation. So we integrate left and right hand side. So we assume that the small d is the momentum deficit for this small area, and when we integrate it, so it will show the total momentum for this area. So we just change the terms. So this is not the integral rule. So this is just our definition. So the small d will become capital D to show the total momentum deficit. And then we integrate from 0 to delta. So we know that the rho and b here is constant. So we take it out from the integral process. And then we could solve this one. So just to simplify this one, so we times with u square over u square. Okay, so and then we bring this u square to the inside the integral area, and finally we could have develop equation of this one. And then from previous calculation, we know that the integral of 0 to delta u over u 1 of minus u over u dy is equal to theta. And then we could simplify our terms, become this one. Okay. So and then to simplify the calculation, so we just differentiate it to dx. Now we have dx equal to rho bu square d theta dx. So this is just to ease us to equalize with another terms after this. So and then so this is what I said previously. So we must know that the momentum of losses, why the velocity distribution become like that one, because the viscosity of the viscosity of the fluid and its shear stress create that phenomenon. So we could say that the momentum losses, okay, so it is actually caused by the shear stress. So because momentum is a part of force, so we could write that dd is equal to tau and dA. So and then we have tau here and a here, okay, so it's actually the b, the width, time the dx. So here if we could see from here, so this is the b is width, so b is equal to width here. So and then this is y-axis, so that's why we have dy here, and this is an x-axis. So it means the area is x and times b, the width. So that's why in this situation we substitute the dA here with b and dx. So we have this one, and then we bring the dx to the left hand side. So we have dd over dx is equal to tau and b. So and then that's why in the previous term, okay, we change the value here with dx because we have the ddx over here. So what we do now is, because we have two terms, so we equalize these two equations, mean equation 2 and equation 3. So and then We could say that rho b u square d theta dx equal tau times b, and then we could cancel the value of b. So finally, we could write the value of tau is equal to rho u square d theta dx. And again, please make sure that you understand that this u is the capital U, means the velocity of the free stream velocity, not the local velocity. Okay, so this equation is the von Karman equation, the shear stress by defined by von Karman. So another thing that you need to understand is, so Newton's also proposed a law of viscosity that we learned previously, so which is tau is equal mu du dy. And again, I hope you can understand that in this situation, we will take the condition is y is equal to 0. So why we take y equal to 0? Because at y equal to 0, the shear stress is in maximum condition. Okay, so here we already have two equations, tau from the von Karman and also tau from the Newton. So please remember this one because we need to use this in later calculation. So tau is equal rho u square d theta dx and tau equal mu du dy at y equal to 0. Okay, let's say we go for the example here. So we go for the polynomial profile. Okay, for example, so polynomial means the velocity distribution has the power of 2. Okay, so means that u, let's say from the question, it is given that u over u is u y over delta minus y over delta by the square, like this. And we need to calculate we need to determine the boundary layer thickness and the drag coefficient in laminar boundary layer. So now we are focusing on laminar boundary layer because, as I said in the first chapter, at the beginning of chapter 4, so boundary layer also has laminar and turbulent region. So for this one, we are calculating the boundary layer in laminar region. So now we are going to calculate the boundary layer thickness because, as I said, boundary layer thickness is the physical thickness. So mean we could measure it by experimental as well as we could prove it from our calculation. And then we need to calculate the drag coefficient because the drag coefficient will lead us will tell us about the drag force and the lift force again, and we could calculate the lift force after this. Okay, so it is given from the question. It's a polynomial profile, so we have this one. So let's say the velocity distribution is 2y over delta minus y over delta square, and we know the equation from the von Karman is this one, and we know the equation for shear stress introduced by Newton as this one. Okay, so first, okay, the first trick is we solve this by using the shear stress from von Karman. Okay, so it starts from this equation. So, and then from this equation, we know that we have the value of theta. So what we need to do is we need to determine the value of theta. So in previous slide, so I already give you a few an example to calculate the value of theta. So let's say we have the equation of theta is like this. So we substitute the value of u over u with this velocity profile. You do the integral from delta to 0, and then you will get the theta is equal to over 15 delta. Okay, so and then what we need to do, we use this value and we substitute into this theta. So and then we have tau rho u square d theta dx. So we substitute the theta here with 2 delta over 15. So then we name this equation as equation number 1. So and then we have another equation by Newton. So we have tau mu du dy at y equal to 0. So then we need to solve this equation. So in this equation, we have du dy. So means that we need to solve our equation of velocity here, u over capital U. We need to du dy this equation. So I think you know how to do this. So you will get du dy is equal 2u over delta minus 2uy over delta square. And then please not forget to solve that equation with the condition of y equal to 0. So that's why it is good for you to write this equation with its condition of y equal to 0 here. So then we substitute the y equal to 0 here. So finally we get 2u over delta. And then this is the most simple mistake conducted by students. So students assume that this 2u over delta is the value of tau. No, this is not the value of tau. This is only the value of du dy at y equal to 0. So tau is equal to mu du dy over at y equal to 0. So you need to write as this one. So mean you need to write mu 2u over delta. So please bear in mind about this, because this is just the beginning of your calculation. If you make mistake here, so might be you will lose a lot of marks, because this simple careless mistake is it cannot be forgiven. So this is a very simple calculation. So I hope you do not make mistake at this stage. So now what you need to do is we equalize for equation 1 and equation 2. So we equalize the terms that we get from the von Karman with the term that we get from the Newton. And again, please understand that we are going to calculate or to determine the value of delta. So you could see that in this equation, the terms of delta here is now exists. So what, and then if you see the way of this equation, so we have the term of d dx and so on and so forth. So means that we need to integrate this term, so then the value of differential will be disappear. So the trick is we put the something about delta on at the right side, and we bring dx to the left side. So means that we only have one delta here. So and then we assemble the delta and delta star in left hand side. So and then we bring all the terms at the right hand side here. So now we could simplify this, become 15 mu over rho u dx. So this is delta over d delta. So then you know what to do, because we have the d delta at the left and we have dx at the right. So we integrate both sides. So we will have integration of delta d delta and integration 15 mu rho u dx. So this will give us delta square over 2. And here will give us another value of x. So we have a 15 mu x over rho u plus c. So and then we need to determine what is the value of c here. So we assume that we substitute with the boundary condition. So you know that the boundary condition is something like this. So the boundary condition, it's reflects. So it's same with the what we learned previously in chapter 1 to 3. So for example, we have a plate here. So boundary condition means we need to take the condition at the boundary of this situation. So here the boundary of this situation is at this point and also at this point. Okay, so and for this one, the trick is it is good for us to take the boundary at the beginning of the boundary layer. So that's why we take if x equal to 0, and for sure the boundary layer is not developed yet. So the value of C will become 0. So this is the meaning of this one, and this is the actual condition of that boundary condition. So and then we know that the value of C is equal to 0. So we rearrange, we get the delta square is equal 30 mu x over rho u. And then we need to rearrange this term. Okay, please make sure that you have capability to rearrange that term to represent a Renault number, because this is the common action by engineers who conduct with boundary layers and also with conduct with fluid research. So we always use Renault number to reflect the velocity later on. Okay, so how to do this is, okay, if you see this equation, so we have a 30 mu x over rho and u, and we know that Renault number is rho u x over mu, and we found that we do not have any x here. So what we need to do is we just put an x, we time this term with x over x. Okay, so and then rho u x over mu here will reflect the Renault number, and x times x will reflect x square. So that's why from this term, okay, we multiply with x over x at this stage, and then finally we could get 30x square over Renault number. And then this is the value of delta square. And then finally we could say that delta, so we square root all the terms here, so we will get is 5.48x over square root Renault number. So this is the delta, the boundary layer thickness that occur for that situation. So if you have a flat plate and the velocity distribution is in quadratic equation, in quadratic terms, so the boundary layer thickness delta can be calculated by using this equation. So what is this meaning is, so for example, you have a plate like this, so and then you have a boundary layer of this one. So the x here will reflect the length of the plate. So this is the x axis. So and then, for example, you have the x equal to 1, and then you have x equal to 2, and then at the end here is x equal to 3. So if you want to measure what the boundary layer thickness at this location, so you just substitute the value of x equal to 1 at this term, and then you know that Renault number is rho vd. I'm sorry, in this situation, so we cannot use the Renault number of rho vd, so we have rho u l. So it is because, so if you see here, so we have rho u x, so x here means the length of the horizontal plane, so it's become rho u x over mu. In some textbook, they will write this Renault number is rho u l over mu. So L is sometimes the length of the plate. So and then if you want to calculate the boundary layers thickness for x equal to 1, so you just substitute the value of 1 in these terms. So you need to determine, so what is the velocity here. So the u here, okay, you need to look back into your derivation here. So they use the capital U, means so the velocity here is actually the free stream velocity that occur in this situation. So you substitute all the value here, so you will get the Renault number So then you could substitute in this equation, so you will get the value of delta. And the delta here is the physical value. So means that if you capable to conduct an experimental for boundary layer, so you could measure it. So the simple way is actually there is a lot of method of visualization. One of them is we call it as Schindler or something like that. Okay, so you capture that image, and then you could use the scale from that from your capture device, so you could measure it with how many millimeters. Okay, so means that please bear in mind the unit of delta here is in millimeters or meters, so it will reflect the length. Okay, so for this one, because sometimes you will do the integration and so on and so forth, the value of delta here must be always positive. So if you get the value of negative, so means you make mistake somewhere. Okay, and then normally the value of boundary layer thickness is small. If you get it is around 2 meters or 3 meters, so maybe something wrong in your calculation. So it cannot be so large like that one, according to my experience. So it's small. Okay, that's why sometimes if you try to make experimental boundary layer experimental by using the very small plate, for example, just around might be half meters or 1 meters, and uh, you are conducting the experimental by using there might be wind tunnel or water tunnel. So it is a little bit difficult for you to measure the exact thickness of the your boundary layer thickness, because you know there will some be the turbulent motion, so you will have some bubbles there, so the flow it might be a little bit not steady, so it might be a little bit difficult to determine the boundary layer thickness. So that's another story. So means this is one story, that one parameter that we need to calculate the boundary layer thickness, and then we are going to calculate the drag force. Okay, so how to calculate the drag force? We have two equation of shear stress, because you know drag force is actually the reverse, the resistance that we feel when we move at certain direction. So why we feel that resistance? Because we have shear stress. So the shear stress will create the resistance. So we have two equation of shear stress. One is tau rho u square d theta dx, and another one is showing like this one. So here, please make sure that you use the equation from the Newton derivation. So means that you need to use the shear stress equation from the Newton solution. Why we cannot use this one? It is not because we cannot use this one, because for this equation, okay, the term is still in differential term. So we still have dx and the d theta and dx. So if you want to use this term, you need to solve this term first before you could continue with the calculation. That's why I would like to advise you that it is important for you to choose the terms that we solve from the Newton, because in this term they don't have any differential form. So we don't have any dy dx and so on in this equation. So we could use it straightforward. So we have this term. What we need to do is we substitute the value of delta here. So we know delta is 5.48x over square root of Reynolds number. And then we could have this term. So and then we could, this shear stress, okay, you need to understand that. So if we have a flat plate here, so the shear stress here is the shear stress that occur for one molecule. Okay, so and then we equalize this one with the common drag force equation. So this drag force is actually get from the dimensionless analysis. Okay, the dimensional analysis our pi theorem. So we could get that. That's why we could have tau is equal to CD. I'm sorry, C small d here. So we have C small d here, and then we have 1 over 2 rho u square. So here you must be very careful, because now at this stage we are calculating the local drag coefficient. So what is the means by local here? Means we are calculating only for one molecule at certain point only. So you know that force is equal tau A. So and then force is also can be CD 1 over 2 rho AU kuasa 2 AU square. So and then if means that if we want to calculate the tau here, so tau will become C and small d here times 1 over 2 rho NU square. So that's why we equalize this term with the tau equal CD times 1 over 2 rho u square. So this, and this CD can be from this equation. Okay, we could found that CD is equal to 0.73 over square root Reynolds number. So then we need to calculate the drag force. Okay, so the net we need to calculate the drag force. So now from the previous calculation, we are calculating a shear stress for one molecule. So as I mentioned earlier, we have difficulties to measure the shear stress that occur between those molecules and flat plate. Okay, so our aim is to calculate the drag force, the lift drag coefficient, and so on and so forth. So you know it is come from the components of X and Y. So we have some from the pressure and some from the shear stress. Now, so at this stage, so we are calculating the local shear stress. Now we are going to calculate the drag force. So the drag force mean the shear stress here. The we need to calculate all the shear stress. That's why we use the idea of force is equal to tau and A. So we need to understand that the boundary layer is something like that, and because the boundary layer is increase itself, so mean the shear stress here is actually increasing itself too. So that's why we cannot just multiply the value of tau that we have with the area, because we need to do this with the integral method. So we just assume that we have a small value of one value, or a value of shear stress for one small area, and then we time with the area. So the area is B times dx. So I think I already explained about B times dx. So B is the width here, and dx is the small area of this flat plate. So this is the dx here. So for example, we just calculating the area for this one. Okay, so and then we substitute the value of tau here with what we get from the previous calculation, and then we have b and dx here. So this is the important step that you need to understand. So in our calculation here, we have Reynolds number, and our Reynolds number here is equal to rho Vx over mu. So means that we have terms of x inside our Reynolds number. And if we see our integral equation, so we have dx here. So mean we need to integrate all x term for our calculation. So that's why in this calculation, you need to substitute the value of Reynolds number here with rho ux over mu. So and then we solve this integration. So the limit is become 0 to L. So what is L? So let's say we have a plate like this. So we have a boundary layer. So this is an x-axis, but we assume this is the starting point, the origin. So this is 0. And the last point, the trailing edge here is L, mean the total length of the plate. Okay, so means at this point, at the last point here, we assume that the x is now equal to capital L. So we use the capital L here as our maximum limits. So what we do here is because we have an x term here, we could integrate with the x. So, and then we substitute with the value of L. So finally, we will get the drag force is equal of this one. Okay. However, I hope you could rearrange this equation. Okay. Okay, so it is okay for you not to rearrange that one first. Okay, so this is the drag force that we that occur on that situation. Okay, first, so finally, so instead of drag force, people normally use drag coefficient to solve the problems. So we know that the the relation between the drag force and the drag coefficient is showing like this one. So FD is equal CD 1 over 2 rho AU square. So and then if we want to calculate the CD, so we rearrange the equation. So we have 2FD over rho AU square. And A here is actually the total area of that plate. So for example, we have a plate here. So we assume that the total length is now L and the width here is B. So now we could substitute the value of A here with L and B. So we substitute it with L and B, okay, here. So and then we could get the final terms of CD is 1.46 square root mu rho U and L. And then we could simplify this term, become this term. So what and then sometimes here when you cancel too much, okay, might be you cannot get square root mu rho UL. So please make sure that you need to do something to get your final answer in terms of Reynolds number, because this is the official way to represent your CD. Because in normally if you want to check your CD is correct or not, so you need to show it in terms of Reynolds number. Because so I think previously I already mentioned that Reynolds number is actually the way we reflect the velocity with a dimensionless term. Okay, so and then okay, here before we stop for the first half. So here actually we have a lot of velocity distribution. So in some example we have y over delta, and in this example, so we have quadratic, so y by the power y square. So please make sure that you could do the same things. You could calculate the delta, the CD, and the CD here, this local drag coefficient, and also the drag coefficient by using these three velocity distribution. So these three velocity distribution, I mean, we have five here. So we have power 1, so we have linear, so we have quadratic, so we have by the power of 3, and we have a power of 4 here, and we have the sinusoidal here. So these five velocity distribution is the most common velocity distribution for laminar boundary layer. So it is advantage for you to practice yourself to get the delta, CD and CD here for all this velocity distribution.